Hello there, this is your grammar mathematics teacher, and today we're going to begin the discussion on topic by topic, and we are starting with the theories of indices. Now, for me, this is the concept that sandwiches the elementary school mathematics, or better still referred to as arithmetics, and the senior school mathematics. I recall when I was in primary, was it 3 or 4? We were given stuff like express, say, 72 as a product of prime factors. Way back then, our teacher taught us the simplest one. That's in my own judgment, which is you put something like this. You put the 72 here. You look at the smallest prime number that can go into it, which is 2. You have 2. 2 can go here 36 times. 2 again, it will go 18 times. 2 again will go 9 times. This time around, 2 can no longer go, but 3 can. 3 here, 3, and 3, 1. So we now have 72 equals 2 times 2 times 2 times 3 times 3. Way back then, I'm talking about 1988 or 89. Our teacher told us to write it in what he called standard form, and that is 2 raised to the power 1, 2, 3. 2 raised to the power 3 and 3 raised to the power 2. This is what my teacher then called standard form. But with time, this is not standard form. This is index form. This is index form. What am I trying to say? When a number, say 8, is written as 2 raised to the power 3, it is said to be written in index form, where this 2 is called the base and this 3 is called the power, index, or exponent. So these terms are used interchangeably depending on the interest of the author. So wherever you see power, index, or exponent, as far as mathematics is concerned, they are referring to the number written up when a whole number is written in index form. As you can see, 8 is 2 times 2 times 2. So 8 is now in index form when written as 2 raised to the power 3. The concept of indices is derived from this term, index. The plural of index is indices. And these theories revolve around 2 or more indices. So this is what we have. Having shown or having made reference to what we are supposed to be familiar with, knowing fully well that several other persons would have thrown this to the dustbin of memory, considering the fact that from my experience, most of the time, candidates tend to believe that whatever they have been taught in the previous grade of academics is no longer relevant when they get to a higher grade. So I believe that some persons might have forgotten, but I have brought it to the fore now. Now let's go to the concept proper. Recalling that 8 is equal to 2 raised to the power 3 and 4 is equal to 2 raised to the power 2. We know that 8 times 4 is equal to 32. Suppose we prefer to present 8 as an index number, that is 2 raised to the power 3 times 2 raised to the power 2. We will now have 2 times 2 times 2, that is for the 8, then times 2 times 2, that is for the 4. We are now going to have 2 raised to the power 3 times 2 raised to the power 2 being equal to 2 raised to the power 5 altogether. What do we observe? Our observation is that we would not have needed to line all of this up. It's just a matter of us adding the powers. So then that brought about this concept, which is popularly referred to as the multiplication or product law of indices. X raised to the power n times x raised to the power n is equal to x raised to the power m plus n. In other words, whenever you have two numbers written in index forms, each of the numbers having the same base. Don't forget I mentioned that when a number is written in index form, as in 2 raised to the power 3, the 2 is the base and the 3 is the power or index or exponent, depending on whatever the author prefers to call it. Now, whenever we have two numbers, as in 2 raised to the power 3 x raised to the power m and 2 raised to the power 2 x raised to the power n, if we are multiplying them, we simply retain one of the bases and add the powers. So it is expressly shown here. 2 raised to the power 3 times 2 raised to the power 2 is equal to 2 raised to the power 5. It's now left for us to confirm. Is 2 raised to the power 5 going to give us 32? Let's confirm. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So this is a shorter way of arriving at the solution. Now, like I tell whoever cares to listen, mathematical principles are designed to arrive at solutions here at systemic level. We have systematic approaches and we have systemic approaches. A systematic approach is a situation where you take a vehicle from here and you are driving to Lagos. You get to Lokoja, get to Ore before you get to Lagos. A systemic approach is when you take a flight from here, you are landing straight in Lagos. So those are the two approaches. So mathematical principles are designed in some cases to make one arrive at systemic solutions, kind of. Now, I'll show an example in which we can apply this concept. So the example will be basically based on our knowledge in the elementary school. Say for instance, if you are saying you are given something like this, given that 3 raised to the power x is equal to 243. Find x. In some cases, you will be told to solve. If you are simply told to solve, 3x, 3 raised to the power x being equal to 243 is still in order, because the fact remains that the presence of this equality sign makes it an equation. In a problem like this is not supposed to take up to or more than 15 seconds. How? If you are familiar with this, you will know that the first thing you do is to express this also in powers of 3. And you say it implies 3 raised to the power x is equal to 3 raised to the power 5, because 3 raised to the power 5 is going to be 243. 3 raised to the power 2 is 9, raised to the power 3 is 27, raised to the power 4 is 81, raised to the power 5 is 243. So, in an equation, if you have the left hand side being equal to the right hand side, then the equation is said to be consistent. The bases are equal. The powers are automatically going to be equal. Therefore, x is equal to 5. Now, this problem can only be found, as far as I believe, can only be found in an objective test. Apparently, I extracted it from an objective test. WAEC. I don't know if it's WAEC or NECO now. I extracted it from an objective test. So this is it. Now, this is how something like this could be applied. Suppose on the other side, on the other hand, we are given 32 divided by 8. Of course, we know that it is supposed to be 4 ordinarily. Assuming that the presenter or the examiner does not want to express 32 as an integer, but as an index number, and he writes it as 2 raised to the power 5 divided by 2 raised to the power 2, or 3, forgive me, 2 raised to the power 3, meaning that 8 has been presented in index form and 32 in index form. What do we do? It simply implies 2 times 2 times 2 times 2 times 2 divided by 2 times 2 times 2. Our elementary mathematics suggests that we cut it out with the highest common factor. And this is 1, 1, 1, 1, 1, 1 times 4. And that gives us 4 over 1, which is still 4. It is not different from this. But the fact that we have this as 2 times 2, it now means 2 raised to the power 2 is equal to 4. So we would have presented this as 2 raised to the power 5 divided by 2 raised to the power 3 is equal to 2 raised to the power 2. Now, one thing I am trying to establish here is the fact that this does not negate the fact that 32 divided by 8 is equal to 4. And that is what I have tried to establish here by writing this 4. This 4 would not have been necessary, but I am just trying to establish for the purpose of empathy. Now look at this. That brings about this other rule, which is called the division rule. X raised to the power m divided by x raised to the power n is equal to x raised to the power m minus n. Now, the previous rule or law or theory, as the case may be, is if we have two index numbers and that are being multiplied, as long as both have the same base, we return one of the bases and add the powers for multiplication. This one, if we are dividing, we return one of the bases and subtract the power of the divisor from that of the dividend. Now the other one, there was no need for me to talk about which one to subtract because addition is commutative. And what does that mean? Commutativity is when the order of arrangement of the terms involved in an operation does not affect the result. How do I mean? 2 plus 3 is equal to 5. If another person prefers to add 3 to 2, it will still be 5. So the arrangement does not affect the result, and that is what commutativity means in mathematics. So let's have an example with the application of this law. Example 2. Solve 9 raised to the power 2 minus x being equal to 3. From what we have here, we will just recalling that x raised to the power m divided by x raised to the power n is equal to x raised to the power m minus n. It implies that 9 raised to the power 2 minus x is equal to 9 raised to the power 2 divided by 9 raised to the power x. Because when the same bases having different powers are to be, one is to be divided by the other The power of the divisor is subtracted from the power of the dividend. Now, if we have this one is already in the form of the right hand side. Now, it's important to understand that theories or laws are not meant to be one way. And that's one of the things that people don't understand when it comes to mathematics. They think that the theories are one way. No, it could be either ways. Now, we have this in form of this. We are at liberty to bring it back to this form. And that gives us this, which equals 3, because we're told is equal to 3. So this is the left hand side that we have just decided to demystify. At this point, this is over 1. So we can now cross multiply, and that implies this times this will give us 81 being equal to 3 times 9 raised to the power x. So if we divide both sides by 3 first, (27) being equal to 9 raised to the power x. At this point, it is important that I deploy another law that I have not explained, which is, we express this in powers of 3. This is going to be 3 raised to the power 3, and this is going to be 3 raised to the power 2, talking about the 9, then raised to the power x. So it will be equal to, this is 3, it gives us 3 raised to the power 3 being equal to 3 raised to the power 2x. So if the bases are equal, the powers are deemed to be equal. It implies that 3 is equal to 2x. We need x. Therefore, x is equal to 3 over 2. This is one of the occasions where, very rare occasions, where an answer being a fraction is allowed or permitted to be written as an improper fraction. However, it is important that you do your best to write it in the simplest form possible, 1 whole 1 over 2, characteristically equivalent to 1.5. Even if the examiner does not need it, you never can. But in this, it takes care of this. Now, the second law that we just discussed, which I call the division law, that is x raised to the power m divided by x raised to the power n is equal to x raised to the power m minus n. The question that will readily come to mind is the fact that would it always be that m will be greater than n? That is one. Or is it not possible for m and n to be equal? Let's first address the scenario where m and n are equal. Consider 2 raised to the power 3 divided by 2 raised to the power 3. If we are given something like this, it implies, and we want to apply the law. If you are told to evaluate, now this is what you do. 2 raised to the power 3, by reason of this law, they have the same base and we are dividing them. We simply subtract 3 from 3, and that gives us 2 raised to the power 0. Now, to some persons, anything associated with 0 is 0 or a nullity. But that is not true. Like I said earlier, that mathematical rules are not meant to negate the already existing arithmetic principles. So, It's simple. From our elementary school, we have heard that any number divided by itself is equal to 1. So that has not been negated. The fact that this presents itself as 2 raised to the power 0 still has not negated that. We now come to say 2 times 2 times 2 divided by 2 times 2 times 2 is going to give us 1 over 1. Therefore, the other law, x raised to the power 0 is equal to 1. Now take note, even if it is 766 put in bracket raised to the power 0, and you understand that the concept being discussed is not angles, the value is 1. It just suggests a situation whereby a particular number has been presented in index form and it is made to divide itself. That's what it means. So 2 raised to the power 2 2 raised to the power 0 therefore is equal to 1. So this is another law of indices, making the third one that has been discussed. In this case, this is likely to be found in objective test. You'll be given a particular number raised to the power 0. You should know that it is 1. On the other hand, you may be solving a particular problem, and at the end of the day, it gives you something raised to the power 0. You rest assured that the final answer is 1. Having mentioned, I will write all the laws on the summary section. So we have another one. Suppose we have 9 raised to the power 2 times 9 raised to the power 1 equals 9 raised to the power 2 plus 1 by reason of our initial law. X raised to the power m times x raised to the power n is equal to x raised to the power m plus n. So suppose we understand that both the bases could still be expressed as, in powers of a smaller number as it's obtainable here. This is 3 raised to the power 2, 9 itself is 3 raised to the power 2. Now, this one alone is this 3 raised to the power 2, then raised to the power 2, times 3 raised to the power 2 for this 9, then raised to the power 1. We are now going to have 3 raised to the power, this time this will be 4, 3 raised to the power 4. In other words, we could still have obtained this 3 raised to the power 4 in the form of 3 raised to the power 2, taking the whole of these now as the base and this as the power. If we expand it, we have the 3 raised to the power 2 squared, so to speak. This is our base now, this is the power. So when we split it up, it gives us this. And when we apply this law, it gives us 3 raised to the power 4. Now, times 3 raised to the power 2 raised to the power 1, so it still remains the way it is. Having established this law now, we now have it to be, we simply add, if we do these two first, it gives us 3 raised to the power 4, that is 2 plus 2, 4, then plus 2. And that is going to give us 3 raised to the power 6. What we will now consider is, with this value, this value, will it give us the same value as this? Now, let's see. 81 times 9 is going to, it's 729. Equals 729. And let's remove 81 from 810. That will give us 729 or so. So we do the same for this. We try to find the value of 3 raised to the power 6. That is going to be 243 times 3. And that is going to give us 729. Good. It's 729. Equals 729. Hence, the other row x raised to power m in a bracket raised to power n outside the bracket equals x raised to power the power in the bracket times the power outside the bracket. This is the other rule. And let me state for the records that there is no limitation to what the value of m and or n could be. In other words, it is not important that the powers must be integers. That's on one hand. It's not also important that the powers must be positive numbers. It is not important that the powers must be whole numbers. It could be decimal numbers. It could be just anything. So the most important thing is to understand the rule and apply it where it's observed to be applicable. And how do you easily detect where it is observable? It's applicable. It is by consistency, like I promoted in one of the previous videos. Having said so, let's go back to the other theorem. We have deduced one other rule from the first one, the multiplication rule. We have deduced one other rule from the division rule. More could be deduced from the division rule. So let's take that. Then we'll come to this again. I asked two fundamental questions about the division rule. That one of the things that will come to mind is it not possible for, as it's obtainable here, x raised to power m divided by x raised to power n. We have talked about one of the questions, the fundamental questions I raised. Is it not possible for m and n to be equal? And we have taken care of that. Now, for m to be 1 less than n, as in 4 divided by 8, presented as 2 raised to power 2 divided by 2 raised to power 3. And that implies 2 raised to power 2 minus 3, which is going to be 2 raised to power negative 1. What does it portend? Suppose, like I always make reference to our elementary arithmetic. This is what we have. It implies 2 times 2 divided by 2 times 2 times 2. This here 1, this here 1. This here 1, 2 here 1. We are now left with 1 over 2. Therefore, 2 raised to power negative 1 is equal to 1 over 2. And that takes us to this specific rule. X raised to power negative 1 is equal to 1 over x. This is another law of indices. I said specific because we still have a general one that also covers this. That is an instance where m is not just 1 less than n, but much more less than n. In other words, it could be, say, 2 divided by 16, which could be expressed as 2 raised to power 1 divided by 2 raised to power 4, and that gives us 2 raised to power negative 3. So this one now we are going to apply the general one, and that is going to be x raised to power negative n is equal to 1 over x raised to power n. So these two laws are about the same as far as I'm concerned. If you understand this, you can always apply it here, because this is still as good as x raised to power 1 there, but the negative has been taken care of. So this is the general one, and this is the specific one where the power is precisely negative 1, and this is the general one where the power could be just anything as long as it's bearing a negative. You are going to take the reciprocal of that, and the negative will be taken care of. How did we arrive at this? Now let's do this. 2 divided by 2 times 2 times 2 times 2. This here 1, this here 1. And we now have it to be 1 over 2 raised to power 3. So you can see now that as soon as the negative is taken care of, the reciprocal is taken, the negative is taken care of. 2 raised to the power negative 3 is 1 over 2 raised to the power 3. So this is another law of indices. I have made, okay, 5th or the 6th? 5th. Good. And that takes care of this. Suppose we are given, recall from this previous law, x raised to the power m raised to the power n equals x raised to the power m times n. Suppose that we have a number, say evaluate 9 raised to the power half. We have never had instance like this directly from the explanations we have done so far. However, what should come to mind is the fact that 9 could be expressed in powers of 3. Luckily enough, the power will be precisely 2. So it implies 3 raised to the power 2 in the bracket, then raised to the power half. At least we have depleted 9 reasonably true in accordance with mathematical principle. And that's one of the things I tell whoever cares to listen, that it does not matter how seemingly complex any mathematical problem is. What is important is you just start something, take a step, and you will see the brighter side as soon as you take a step. Now look at this. This will immediately call to mind the possibility of we multiplying this by this. You now recall x raised to the power m raised to the power n equals x raised to the power m times n, which will now imply 3 raised to the power 2 times 1 over 2, and that will give us 3 raised to the power 1. Now this is in its simplest form. What is the relationship between 3 and 9? To many, 3 is the square root of 9, at least the positive square root. Okay, let's test another one. Consider an instance where you are told to evaluate, say, 27 raised to the power 1 over 3. Or even before that, let me derive this specific 16 raised to the power 1 over 2. Also, like I did with 9. The next thing that should come to mind is the possibility of 16 being expressed as 4 raised to the power 2. It implies 4 raised to the power 2 in bracket, then times half. Then we still make reference to this law, and that will give us 4 raised to the power 2 times half is going to give us 1. And that is going to be 4. Anything raised to the power 1. Every number, every integer is raised to the power 1 divided by 1 and times 1. So as it is, 4 raised to the power 4 raised to the power 1 is still 4, except you are told to give your answer in index form. That is the basis on which you will write it as 4 raised to the power 1. If not, 4 raised to the power 1 is as good as 4. So what is the relationship between 4 and 16? 4 is the square root of 16. 3 is the square root of 9, like we obtained in the previous one. Hence, this other law. X raised to the power half is equal to the square root of x. So whenever you are given a number and it is raised to the power half, you are finding the square root. It's as simple as that. So, having obtained this, then the general one. This is the specific one where we have the precise x raised to power 1 over 2 means the square root. I was going to do x raised to power, I was going to do 27 raised to power 1 over 3. It will still have arrived, it would have given us this other law, general, for the purpose of time. If you have any question, feel free to send a comment or send the question in the comment, or you can call the number that will be provided for you. So x raised to power 1 over n is equal to the nth root of x. So where you have x raised to power 1 over 2, then you are finding the square root. If it is 1 over 3, you are finding the cube root. If it is 1 over 4, you are finding the fourth root of the number in the bracket. So that takes care of that. We have one more, I think, yes, one more to go. So I will, after this, list all the laws and solve one more problem and make a few more remarks on the generality of the applicability of those laws. Now, let's consider a situation whereby we have something like this. Evaluate 27 raised to power 2 over 3. Now, this is a dicey one. Dicey one in the sense that this presents itself in the form x raised to power n times n. And someone might want to ask, how do I know? That is because I know that 27 raised to power 2 over 3 can be expressed as 27 raised to power 1 over 3 then times 2. Because if I multiply 2 by 1 over 3, it will give me 2 over 3. Now, it's important that one exhibits a very high level of ingenuity when it comes to solving mathematical problems. But like I tell whoever cares to listen in several of the previous videos, it does not come by wishes. It has to come by reason of your consistent interaction with this, and it becomes natural for you to see what several other persons will not see as soon as a problem is presented. Having said so, it occurred immediately to me that this could be split into two, 1 over 3 and 2. So, having split it into 2, it now suggests to me that I will simply find the cube root of 27, which is possible, then I'll square it. And that is going to give me 3 raised to the power 2. If I am not told to leave the answer in index form, then it's going to give me 9. Even if I'm told to give it in index form, I can write it like this, as long as it's an essay question. The examiner has a duty to mark you right as soon as he has followed your correct steps to the final answer. Every other thing you write after is irrelevant, and he cannot penalize you for that. That is why I do say that it's a lot more easier to pass mathematics than to fail, because the examiner has a duty to follow your correct steps to where the final answer is. Every other thing is a waste of your time. That is the, it's enough a penalty for you. So he doesn't have to put any more burden on you. So that takes care of this. Having said so, I now want to put down all the laws now. Not in any important order.
x raised to power m times x raised to power n is equal to x raised to power m plus n. The next one, x raised to power m divided by x raised to power n is equal to x raised to power m minus n. Another one, x raised to power 0 is equal to 1. The next one, x raised to power negative 1 is equal to 1 over x. The next one, x raised to power negative n is equal to 1 over x raised to power n. 1, 2, 3, 4, 5. X raised to power m into n is equal to x raised to power m times n. X raised to power 1 over 2 equals the square root of x. And the general one, x raised to power 1 over n is equal to the nth root of x. The last but not the least, x raised to power m over n is equal to the nth root of x, then everything raised to power m. And that's what I did with this one. So this is as good as the cube root of 27 then raised to power 2. So these are all the laws of indices. This one covers 1 over 3, which implies the cube root of, 1 over x raised to power 1 over 3, which means the cube root of whatever is the base. And that takes care of all the laws of indices. These are the laws of indices. Now let me state for the record that it is not important for a problem to require only one method one law for solution. A problem may require up to 3 of these before you arrive at the final solution. I'll solve this example, and I think this covers it to a reasonable extent. Then subsequently, any other question that anyone has may be forwarded to the dedicated WhatsApp number. Say for instance, you are told to, now a problem on indices, it may come in form of equation, it may also come in form of expression. This one is coming in form of an expression. Say for instance, this is example 3, the one that is not based on attempt to derive the formula. Evaluate six into 1 minus 7 over 16. Forgive me, this space is not enough. Evaluate 6 into 1 minus 7 over 16 raised to power negative 1 over 2 times 2 raised to power negative 1. So this is it. Having been given something like this, the first thing that should come to mind, like I have said earlier, problems requiring the application of indices laws may not necessarily come in its simplest form. It may require a few conversions here and there. This one is even somewhat compounded because it has another fraction. So it implies the first thing we are supposed to take care of is the application of this order of operation. Big mass. That is because there is no of big mass. We have bracket, we have indices, not only one. Index. So we take care of that. Those before no division, then multiplication, no addition, and so now this is subtraction. But because it's in the bracket, it takes precedence. So we just have to address it immediately. That means we are going to have 6 into. Now, by reason of my interaction with such numbers as this, immediately I should know that every time you are subtracting a proper fraction from a whole number, particularly 1, all you need to do is to find what do we need to add to the numerator to equate it to the denominator. In this case, it's 9. So if I am subtracting 7 from 16, I'll be left with 9. That is because this is as good as 16 over 16 to obtain equal denominator. So we now have everything in this bracket now will simplify to 9 over 16 raised to power negative 1 over 2 times 1 over 2. Not forgetting that x raised to power negative 1 is equal to 1 over x. 2 raised to power negative 1 is equal to 1 over 2. That takes care of this. That is because this and these are supposed to be addressed at the same time. Index. And particularly because this one does not affect this. So that's why I've addressed that immediately. Now let's address this index. It implies 6 into. The same rule that applies to this applies to this. And that becomes 1 over 1 over 9 over 16, which is going to be 1 over 9 over 16 raised to power half, then times 1 over 2. Not forgetting that x raised to power half is equal to the square root of x. Let me outline it so that you can see that this is an application. So it now implies that 6 into the square root of this half will no longer be there. We now find the square root. But because of this one, the reciprocal of a fraction is an inversion of the fraction. So I will now bring this 4 up. 16 over 9 now, then times 1 over 2, and that gives me 6 times 4 over 3 times 1 over 2. So this reduces this to 2. This reduces this also to 2. So I now have 2 times 2. But because it's an index, it's an indices problem, I can decide to write it as 2 raised to power 2. I'll still equate it to 4 just in case the examiner wants me to. And the fact that I am told to evaluate, this is the numerical value of all these gigantic expressions. So this is one of the applications. Like I said earlier, it's important to interact more with these concepts to be able to identify wherever it's applicable. I did not bother to write this out because I do not have enough space to write here, and particularly because I have the laws on the board. So this is how we put an end to the discussion on indices. Now, if I want to solve any problem that involves indices now, it's just a matter of me making reference to any of the law, having discussed it, and having made remarks on the fact that it is important to interact well enough with them to know where and how to come in whenever a problem is given. For further inquiries, like I said, the dedicated WhatsApp line could be, engaged. Thank you. Like, subscribe, and share.